There we go. Right. So our final speaker today is Ben Torsney from University of Glasgow, and he's going to be talking about optimal design, Lagrangian and linear model theories.
Okay, thank you very much for the invitation to attend. I hope you will still be able to understand me, although I don't come from England. Apparently, according to a survey reported yesterday in a paper called The National, which supports a certain kind of policy in Scotland, the Glaswegian accent is the most easily recognised. According to some Expedia group who have produced an accent map, 78% regularly and correctly recognise Glasgow, whereas received English is only down at 74%. Okay, this is quite technical. It's something I've been working on for some time, but I have recent results which I think brings it to near a conclusion. So there are two main topics. First, discussing optimization problems, and then the use of a multiplicative algorithm. And the general problem that I want to consider is that the maximization of a criterion phi when the variables forming the vector p must satisfy a linear constraint, a t equals b, and also be positive. If we write down the Lagrangian for this problem and set the derivative of the Lagrangian to 0, then what we find is that the vector d of partial derivatives must exactly equal the matrix P times lambda, where P is the transpose of the matrix A defining the constraints. Must be satisfied exactly. And if we consider a linear model, where the expected value of vector d is B lambda, then the implication would be that the zeros, the residuals, should be exactly 0 under this model for the data B. Given that B is equal to the matrix A transpose, and if we let the matrix W be symmetric, then a weighted least squares estimator of the vector lambda under that fitted model, the residuals would be I minus HD, H, the standard hat matrix. And if we let S be I minus H, H defined there, what we're saying is that the vector F of residuals should be the matrix S times the vector D. And a key feature is that S transpose P multiplied by A should be 0. Now this result, a key point of what I'm now going to say is that this result implies that the vector F of residuals are playing the role of directional derivatives, which were introduced for the design problem. So consider the standard optimal design problem, which is a special case of the constraint of a single linear constraint that the p's should sum to 1. The equivalence theorem states that these terms fj, which is the partial derivative pj minus the sigma pidi term, should be 0 for positive pj, and of course in the design problem there could be 0 pj, and in that case these directional derivatives should be less than or equal to 0. So fj I've called a vertex directional derivative. Now, just to remind us, the definition of such a derivative of phi at p in the direction of q, where q is also in the constraint space, has this formal definition, but if phi is differentiable, that definition, the directional derivative p to q is sigma si di, where the si's are qi minus pi and therefore add up to 0. So, given the constraint is satisfied by P and a vector S component sum to 0, so that S is in the null space of our constraint defining vector of 1s, and 1 transpose P plus S equal to 1, we have in this term f p plus s equal to s transpose d, a derivative of phi at p in the direction s. The original definition was defining derivative at p in the direction of another point q, which would normally be in the same constraint space. Now we've just changed things slightly. It could be that we could have some components of p plus s negative, but for our purposes it suffices that p is positive and q positive normally, but that wouldn't be necessary, and that for some small alpha, p plus alpha s is greater than 0. Going back to our directional derivatives, vertex directional derivatives, with ej that gets me a vector, fj is f of p towards ej, and the vector s is then of the form f p plus s, where s is ej minus p. Consider the Lagrangian for this problem. It is phi p minus lambda times sigma pi minus 1. Set the derivatives of the Lagrangian to 0, we get the derivatives of g minus lambda, and of course the derivative with respect to lambda is the sigma pi minus 1. Necessary for order conditions are that the Lagrangian derivative should be 0, therefore the dj must equal lambda. All the partial derivatives share a common value. And although it seems strange, and I have a comment from Whittle about this, the implication is that dj is equal to lambda, and in the Lagrangian approach you normally come up with a formula for lambda and then substitute that back in to find out solutions for the original variables. So there are many solutions, linear solutions for lambda in terms of the partial derivatives di. Sigma wi di, where wi is any set of weights summing to 1, which could be negative, some of those could be negative. And here are some examples. The natural one to consider is just uniform weights, which would mean lambda was the average of the partial derivatives of phi. Or w equal to a particular unit vector would give lambda equal to dt. And in effect, you would be making that choice if you chose to deal with the summation constraint, sigma pi equals 1, by substituting for pt in terms of Yells. Another one would be, the median of the dj's. And of course, the one that the equivalence theorem chooses is to take these w's to be the variables pi themselves. We let fj be dj minus lambda and lambda sigma wi di, then we have fj equal to s transpose d, s being ej minus w, and 1 transpose s equals 0. So fj equal to p is equal to p, a directional derivative of phi at p in the direction of s. All of these w's define different directional derivatives. And a linear model connection, if we consider a linear model where the dj's are random variables with respect to value lambda, we would know that the average of the d's will minimize an ordinary least squares criterion so that the residuals would be dj minus dr. Under such a linear model, the median would minimize the sum of the absolute differences. If we go for a weighted least squares, then we would get residuals equal to dj minus sigma wi di. The general implication is that residuals, for whatever choice of lambda we go for, are all directional derivatives. And coming back to our general problem, and repeating the other slide, we have f equal to the matrix S, vector f equal to matrix S times D, and this result AS transpose equals 0. If we let S be the jth row of S, and therefore the jth column of S transpose, we have in a particular component Fj that it is equal to S transpose D, and AS is equal to 0. S is in the null space of A, AS equal to 0 implies A plus P S equal to AP equals B. We let Fj be S transpose D. It is a directional derivative at P in the direction of S. In general, for this kind of development, we would want Q to belong to S, and for the definition of Fp, Q and S in the null space, the vector S in the null space of the set S. But again, it could be, and this will happen for some of the choices that we are going to encounter, that some of the components of P plus S could be negative, but as long as P plus alpha S is positive or small alpha, we are, so that P plus alpha S is in our convex constraint region, as well as P and Q, that is fine. At this point, I could indulge in a graphical digression, which is on my stick, but time doesn't permit. But it would it mainly involves looking at triangles and working out what all the different choices of lambda, what choices of directional derivative they are selected. Our problem, this general problem that we have considered, is in fact an example of the design problem, because it's a convex region with extreme points as its vertices, and therefore any point in it would be a convex combination of the basic feasible solutions. So we could convert our problem to the general problem to problem P1, but the number of basic feasible solutions could be large, and so that would be unwieldy. In fact, Radoslav Harman has considered an example of this problem, an optimal design problem, whereas in addition to the summation of the weights to be 1, he has introduced a cost constraint. He has approached the problem by coming up with some very imaginary transformation, non-linear transformation between the convex weights of the feasible solutions and what is our variable P. Mysterious transformation. So an optimal design problem could, with cost constraints, would be an example of what we're considering. But the implication would be that the equivalence theorem could be invoked to establish optimality, at least for a concrete criterion. And if you're mystified by all this, don't worry, so was Whittle, or suggesting that Whittle suggests that others might be mystified by it. It is not surprising that people who have known no other would find the Lagrangian multiplier a somewhat mysterious notion to the end of the days. That's on page 25 of his book on optimization under constraints. So that's the first section over. We have this general constraint optimization problem, a set of linear constraints, but it turns out that residuals, what we would call residuals under the linear model, are playing the role of directional derivatives. Now, how to solve that problem? Well, for the P1 problem, I and others in Glasgow have developed what we call the multiplicative algorithm, and it involves a function f with two arguments z and delta. Delta is a kind of tuning parameter which will neither be positive or negative. The derivative f should be increasing in z, and if we set delta equal to 0, we want a constant. And two examples that we will use are the f being equal to the normal CDF with argument delta, capital vector and capital Z, or d to the power delta when d is positive. And the algorithm, this multiplicative algorithm, is of this form. We take current weights, multiply them by this function f with argument z, j, at current iterate delta, and z is either d or f, and then scale so that we have summation to 1. And it has been shown that the directional derivative at PR in the direction of PR plus 1 is greater than equal to 0. We are moving, if we move from PR to PR plus 1, we're moving in an upward direction. Well, I've repeated this. The one choice of f for a general problem would be the standard normal CDF with argument delta f. And then there's a choice for D positive. And there might be a case for standardizing the vectors D by D over lambda for some average version of D for numerical stability. In some cases, under this algorithm, for simple examples, you can change the optimum in one step. So for this algorithm for problem P1 with the constraint is just that we have a set of weights summing to 1. There are two steps. There's a multiplication step, and then there's a scaling to through division of this to get our constraint net. It is now discovered that we can generalize this algorithm to our general problem. And there's these two stages. First, the choice of the multiplication step, choice of Z and F. One choice is to take Z to be our residuals and the little f to be the standard normal. But there's many other choices. The key thing is that we are the vectors, the terms f could be negative or positive. We need a function defined for both positive and negative values. But the other choice I have established, the other choice for positive D has an extension, the D to the power delta for problem 1 has an extension here. The vector f is to be equal to the matrix S times D, that's its definition. If we want the vector f to be 0, that implies that two vectors are equal, where the vector k is a matrix k times D and vector L matrix L times D, where these are non-negative matrices, and the vectors k and L are greater than 0. So f equal to 0 is implying that Ri equal to ki or Li is equal to 1. F equal to 0 is implying k equals L, therefore this ratio is 1. So in the algorithm, take Z to be the ratio R and Fz to be Z to the power delta, for example. And this maybe wasn't immediately obvious, but it was revealed by considering a particular problem, and we will look at this later on, called the double marginal constraint problem. In this case, a double subscripting notation is more appropriate for the variables, and the variables Pij then basically define a matrix or a joint distribution. And this problem is that you want to maximize phi of the matrix P, but subject to fixed row and column marginal distributions. So row sums equal to Ri, and column sums equal to Cj, and the sum of the R's and the C's should be equal. And normally, we're thinking about data, a likelihood would be, log likelihood would be the appropriate criterion, and would have positive derivatives in this case. Well, if you look at the results, it turns out that the Dij in effect must satisfy an additive model. That's a model involving two qualitative factors. Dij should be equal to alpha I plus beta j, where the alphas and betas are like factors in a linear model. And therefore the residuals under such a model would be given by this expression here. And these four terms are all positive. Therefore, this ratio should be equal to 1. And this is how I first saw that result. Now, so that's dealt with the first step of the first what's called the multiplication step. We want to take current values of our variable p's and multiply them by some function of the residuals. But then we have our constraint to meet. I should say that this is only a recent result. I had worked on other ways of trying to deal with this problem. But consider a vector q, which would be our current iterate value, where the components of q are given by this multiplication step in the algorithm. And we might want Fz 0 to be 1 for any choice of f. Let a matrix D, but a diagonal matrix, the components are equal to the components components of the vector Q, let Q star be this expression here, which in fact is a bit like a Moore Penrose inverse of A times B. And in fact, we could replace vector B by AP if P does satisfy the constraints. And the key result is that this vector Q star satisfies the constraints AQ star equals B. In fact, if we go back to the first problem, our P1 problem, where A is vector 1's transpose, B just a scalar 1, then in fact we get back to our scaling operation for column P1. It might be useful that the constraints AP equals B does include 1 transpose equals 1, but now I'm not so sure. Also, a second property is that if delta is equal to 0 in the algorithm, then Q star has not changed from PR. An implication would be that for small delta, given that PR is positive, Q star should be positive as well. So we have the makings of an algorithm here that we might take the next iterate to be this term Q star for some choice of delta small. But there are questions which I haven't resolved. Is it always guaranteed that PR plus 1 will be positive? Is the directional derivative of PR in the direction of PR plus 1 positive? And how to choose delta? There's the matrix W that I introduced, and what we now do, that has been taken to the identity matrix. Other possibilities are to get around any of these difficulties would be to consider a convex combination of the current iterate PR and this term Q star, and choose alpha subject to the PR plus 1 being positive and the directional derivative being positive, which might mean taking alpha to be negative. But hopefully alpha, the one that is positive, is possible, and in fact it seems to work in a number of examples. And the examples I'm now going to consider are models for contingency tables in 2 and 3 dimensions. 2 problems. In one case, the marginal distributions, univariate marginal distributions are fixed, and in our case, fixed to be uniform. In the second case, the univariate marginals are the same, but when the tables are square. 2 standard problems. The data, we're talking about contingency table data, so that it's appropriate to standardize the data from observed to relative frequencies. The normal criterion would be the log likelihood, but another criterion that's occurred in the literature is a linear discriminant one, and others again are chi-square type conditions, criteria. And the choices that were made for the algorithm are the standard normal CDF times delta z, but the z is vector f, and the z to the delta for the ratio algorithm z equal to a ratio. I've been working with all the choices of how to of delta, and so things can be improved, I think. So consider a square contingency table equal to univariate marginals. So it's an I by I table, relative frequency Rij. We get cell probabilities, which where again a double subscripting notation is appropriate. So Pi is going to Pij, and the cell probabilities are up to 1. The hypothesis of marginal homogeneity is that Pi dot is equal to P dot I for all subsequent values I. It's before and after type data. I'll get more particular example later on. And in particular, the data that Stuart had in biometric app, also Plackett in his book, had subjects, males and females, had their unaided distance vision categorized of both right and left eyes. And so a question of interest is the distribution of the distance vision the same for right and left eyes? Are the 2 marginal distributions the same? So here was the data, 4x4 relative frequencies, table of relative frequencies. The sample size was about 3,000 for, this is for males. And we run the algorithm choosing the initial distribution to be uniform, which satisfies the constraints of the marginal homogeneity. And here's the results using the ratio version of the algorithm. I haven't taken a note of the number of iterations, but they were, I think, at most 150 in the examples I considered. So there's 0 residuals, ratios equal to 1 for the first set of the data, and the same again. Here's the females, same story, achieving 0 residuals and ratios equal to 1 fairly easily. This is a 3. When I initially looked at this data for the females, to simplify things, I reduced the categories to 3 just to make the problem smaller. Also, excluded the diagonals because, as in fact, the diagonals are not affected by the hypothesis. The estimates of the diagonal entries do not change under the hypothesis from the unrestricted maximum likelihood estimators. That is a simplification that could have been used in the previous 4x4 tables. Now here's a 3x3 table. So we've got an I by j by k table, relative frequencies R, cell probabilities P, triple subscripts. The hypothesis that we're considering is that all 3 marginal distributions are uniform. So Pi dot dot is one of our capital I and so on. I concocted an example from an example of Weinberg. He had a 2 by 2 by 2 by 3 by 2 table, and I reduced it to a 4 by 4 by 3 table. And I had to change some observations some counts were 0, so I avoid problems, I changed them to 1s. The matrix A is a 7 by 48 one, and again, a uniform marginal will satisfy the constraints. And here are the relative frequencies. Here are the maximum likelihood estimates. Here are the residuals, and this is using the linear form of the algorithm. Now using the ratio version of the algorithm, 0 residuals, the ratio is equal to 1. And an example of using the other criterion, the linear, one of the others, the linear discriminant, different estimates, and again, 0 residuals, and there's no ratios. The linear discriminant criterion, derivatives can be negative, so on the face of it, the ratio version can be used, although I've now come up with an idea for dealing with that. And here's going back to the marginal homogeneity hypothesis, but for a 3 by 3 by 3 table, sorry, well, a 3-dimensional one. An example that is in Finkelton's book, where there was a panel of UK voters and their voting behaviour was recorded in February 1974, October 1974, and May 79. February 74 was the year that Harold Wilson won a general election, but with a very small majority, so it was the second election that year. And then something different happened in 1979. There were 3 voting categories: Conservative, Liberal and Labour. 560 observations. Again, I changed 2 zeros to 1s. The matrix A is 5 by 27. And we have to, for the marginal homogeneity hypothesis, impose some standardizing constraint, so the natural one is that the p's add up to 1. Again, a uniform initial set of values satisfies the constraints. So here's the p stars. 0 residuals, ratio is equal to 1. Then for the linear algorithm, 0 residuals. The linear discriminant, again, 0 residuals. And a motivating paper, the one that started me off on all this, was that I had been at the ERCIM meeting of the ADO, and 2012. I can never remember what this means. It's econometrics and financial mathematics. And Kariki sent me a paper after I'd spoken to him, nothing to do with design or, let's say, he wanted to find a bivariate distribution with uniform marginals. And when I wrote down the Lagrangian, it dawned on me that the derivatives, the dij's, were satisfying the Manhattan model. One final thing. Here is an example I've used in lectures. 3x4 table, eye colour versus hair colour, and there's the frequencies. Program model is multinomial, and I, as an example of fixed marginals, considered these row marginal probabilities and these four values as column marginal probabilities, purely arbitrary. And again, best to standardize the observed frequencies to relative frequencies. And the initial P0 I took to be this, to be the relative frequencies, which does not satisfy the constraints. And this is one of my earliest attempts with this problem when I hadn't discovered the exact scaling of the formula. But a version of the algorithm has worked with the linear choice and the ratio choice. And the scaling that was done is that given any set of table values, you can always scale the table so that the row margins are fixed or to what you want, or scale so that the column marginals are fixed. And I then thought, well, let's consider a convex combination of those two and choose the convex combination optimally to minimize the deviation from our constraints, and as an explicit solution. And that was a scaling operation, and it worked. For these two problems, and I was familiar with this double marginal constraint problem from work that Mike Titchington did back in the 70s. He had attended, visited the National Sampling Organization in the US, and they often conduct samples, a joint distribution, for example, but they feel they know what the marginal distributions are. And so people like Deming and Stefan had used iterative scaling, which is alternating between meeting the row and the column constraints. That would be an alternative algorithm for this problem. I have sidestepped the issue of what the initial P value should be for the algorithm. Consider problems where a uniform was sufficient. But for a general matrix A, there are a number of operations that we can consider. We could choose P0 to minimize AP minus B transpose AP minus B, subject to 1 transpose P equals 1, if that is one of the constraints. Or in fact, we could apply that to each of the constraints of AP equals B and minimize this quadratic criterion, AP minus B transpose AP minus B. If the constraint can be satisfied, if there are P that satisfy our constraints, and there should be for the problem to make sense, then the solution to this quadratic optimization problem should, well, the minimum value should be 0. So we should be able to find a P that satisfies the constraints. But that can be helped if we impose 1 transpose P equals 1, and that's one of the constraints or one of the others. So that's the story.
Okay, any questions for Ben?
When you said that the problem with the model with the copula function, the Bernstein copula, would fall into your framework, how general could this be, for instance, for other copula functions or families of copular functions.
Yeah, well, yes, certainly discrete distributions we want to fix the margins that we fit directly. I need to look back at the paper, but I can't remember exactly why he was wanting to find this joint distribution with uniform marginals, what the connection was with copular. It was just that when he wrote down the Lagrangian in the paper, I saw this link. Because of the 1-3-1 problem is like the linear model for that is like a model with one factor, the one-way ANOVA model. All the dj's should be equal to one parameter. The expected value of dj is equal to mu. This was just an extension of that. But there would be something to check out.
Any other questions? Right. Well, let's thank all three of our speakers again, and for a really good afternoon.